students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Kinetic Theory of Gases. Right? Let's see, before we start with the chapter, let us see what are the assumptions that we have to keep in mind as we study this chapter. What are the assumptions of kinetic theory of gases? Right? The assumptions of kinetic theory of gases. Now these are the properties that you have to assume that gases possess before we start studying about their properties. First, we assume that gas consists of large number of extremely small particles called as molecules. Gas consists of very large number of extremely small particles known as molecule. Right? So we assume that gas is made up of very small particles called as molecules. These molecules are rigid and perfectly elastic spheres. Molecules are rigid, the gas molecules are rigid and perfectly elastic spheres. Right? Now we also assume that the size of the molecules are very small and therefore they can be considered as point masses. The size of molecules is very small and they can be considered as point masses. Right? Next, we also assume that all the molecules of same gas are identical and all molecules of different gases are different. Molecules of same gas are identical and differ from molecules of other gases. So this is what molecules of gases are made up of. They are extremely small. Gas is made up of molecules. Molecules are extremely small, rigid, perfectly elastic spheres of point mass, which are same for same gases and are different for different gases. Now, the actual volume of the gas, the actual volume occupied by the gas molecules is very small as compared to the total volume occupied by the gas. The volume of these molecules is extremely small. The gas occupies much more space than the space occupied by these molecules. So I can say that actual volume occupied by gas molecules is very small as compared to total volume of gas. Total volume of gas. Okay. Now, the intermolecular force of attraction between these molecules is negligible. Since they are very small, the intermolecular force of attraction between molecules is negligible. Right? Once you have this, now these molecules which are present in the gas are always in a state of constant random motion. Molecules are in a state of random motion. Right? They are always in a state of random motion. Now since they are in a state of random motion, they collide with each other and also collide with the walls of the container. Now, as they collide with the walls of the container, they exert a force on the walls of the container, and that is what is called as the pressure exerted by the gas, right? On account of their motion, the molecules collide with each other. Molecules collide with each other, and the walls of the container they collide with each other and the walls of the container, and the collision of the gas molecules with the walls of the container gives rise to the pressure exerted by gas. And the collision of the molecules with the walls of the container collision of the molecules with the walls of the container gives rise to pressure exerted by gas. Gives rise to pressure exerted by gas. And that's how pressure is exerted by gas. Right? Next, I can also say that the collisions are perfectly elastic. Right? Perfectly elastic means there will be no loss of kinetic energy during collision. Collisions are perfectly elastic. Are perfectly elastic. The collisions that occur between these molecules are perfectly elastic. Now, between two successive collisions, the gas molecules travel in a straight line with uniform velocity. Between two successive collisions, gas molecules travel in a straight line with uniform velocity. Right? Next, I said that they travel with uniform velocity. Now the time of impact, that means the time for which they collide, is very small as compared to the time interval between two successive collisions. Now, even though the molecules are constantly moving from one place to another, the molecular density of the gas always remains constant. Molecular density means the average number of molecules in one space will always be constant. The molecular density of gas is always constant. Right? Next. Now, at constant temperature, the average kinetic energy of the gas molecules remains constant. At constant temperature, the average kinetic energy of gas molecules remains constant. Gas molecules remains constant. So these are your assumptions before you start studying this chapter. So these are the things that you need to know about gas, right? If you are studying about gas, these are the assumptions on which all the theories have been based. Now these assumptions are true for ideal gas, but in practicality, most of the gases don't follow all the assumptions. But when the laws were stated assuming that a gas would follow all these assumptions. Fine, do we get this thing here? Next, what do we understand by mean free path? Mean free path. What is mean free path? The straight line path covered by the molecules between two successive collisions is called as free path. Since the length of the free path does not remain constant, first of all, let's see what is free path. What is free path? Free path is the straight line path, the straight line path covered by a molecule, the straight line path covered by a molecule between two successive collisions is called free path. Now the free path is not going to be same for all the collisions, right? So what is mean free path? It is the average distance covered by the molecules between two successive collisions. So what is mean free path? Mean free path is the average distance covered by the molecules between two successive collisions. Fine, that is called as mean free path. Thus, mean free path I can say is delta is S divided by M, where S is the total distance covered by the molecule, N is the number of collisions. The total distance covered by all molecules divided by the total number of collisions will give you the mean free path. Fine, do we get this thing here? Next, let us derive pressure exerted by a gas. Derivation of pressure.
So you please repeat again what is S?
S is the total distance covered by all gas molecules, and N is the total number of collisions of all gas molecules. Right? Derivation of pressure of a gas. Let's consider that you have a container. Right? Now, let's label the container. This is along x-axis AO. Let's consider that you have y-axis here. This is my y-axis, this is G. Okay, so let's assume that this point is B. So my bottom face is OABG, right, along XY axis. Let's assume that this is my Z axis and this point is say E, right, and the top face is EBCF, right? So this is along X, Y and Z axis. I'm considering a container, a three-dimensional container. Now let us see how much is the pressure and how do I derive the pressure exerted by a gas molecule. How do I derive the pressure exerted by a gas molecule? Now, the molecules of the gas in a container are constantly moving in all possible directions with all possible velocities. They collide with the walls of the container. During these collisions, the gas molecules transfer their momentum to the walls of the container. Right? They have, see these molecules as they are moving, they have mass and they have velocity. When they collide with that means they have momentum. When they collide with the walls of the container, they transfer their momentum to the walls of the container. Right? Thus, large number of molecules undergo large number of collisions with the walls of the container. Therefore, the total momentum that is transferred onto the walls of the containers becomes very large, and this process of transfer of momentum exerts a pressure on the walls of the container. Now we are going to mathematically derive, an expression to find out how much is the pressure exerted. Do you understand why pressure is exerted? The gas molecules are constantly colliding with each other in the walls of the container. As the gas molecules move, they have mass and velocity, that means they have momentum. As they collide with the walls of the container, they transfer their momentum to the walls of the container. Right? As they collide with the walls of the container, their momentum changes. Now if I apply Newton's second law, by Newton's second law, whenever there is a change in momentum, it gives rise to force. That means these molecules, as they collide with the walls of the container, they exert a force on the walls of the container, and this force exerted per unit area on the walls of the container gives rise to the pressure exerted by the gas molecules. Do we understand why gas molecules exert pressure on the walls of the container and how a pressure is formed. So let's derive this. Consider a cube. Let's consider a cube of length L. Let's consider a cube of length L. In that case, I can say that the surface area of each face, of the cube will be nothing but L square, right? The volume of the cube is going to be L cube, right? Now let us assume m is the mass of each molecule. Mass of each molecule of gas. Let's assume that m is the mass of each molecule of gas, and let us assume that there are n number of molecules that are inside the cube. The total number of molecules inside the cube, let's assume is capital N, right? Therefore, what will be the total mass of the gas? The total mass M of the gas can be given by the formula. Mass of one molecule of gas is M and there are n number of molecules. Therefore, the total mass of gas will be M into N, right? Density is nothing but mass upon volume, but mass we found out as Mn upon volume. So the density of gas is going to be nothing but Mn upon volume, right? Now, what we are going to do is, instead of considering the entire container, we are going to consider that the container is divided along three axes: x-axis, y-axis and z-axis, right? Consider three intersecting edges of the cube. Intersecting edges of the cube along x, y and z axis. Fine. Now, the molecules of the gas in the cube are going to move in all possible directions with all possible velocity. Hence, we can safely assume that they exert the same pressure on each face of the cube. Since the molecules of gas move in all possible directions with all possible velocities, hence they exert the same pressure on all faces, right? I can safely assume that they exert the same pressure on each face of the cube. I can write it this way: face of the cube, right? Now, if they are exerting same pressure on each face of the cube, now I have divided the cube along three axes: x-axis, y-axis and z-axis. That means I can safely assume that on an average, same number of gas molecules must be colliding with each face. That is the reason why they are exerting same pressure on each face of the cube. If they are exerting same pressure on each face of the cube, then they should have approximately equal number of molecules colliding with each face. If there are n number of molecules inside the container, that means n by 3 number of molecules should collide with each face of the container, right? So I can say this, we can say that it can be assumed that on an average n by 3 molecules are moving parallel to each of the coordinate axes. Molecules are moving parallel to each axis right? So now I know the number of molecules that will be colliding with each face if I've divided the cube into 3 faces. Now, let us assume, let the velocities of n by 3 molecules moving parallel to say x-axis is say C1, C2, C3, so on up till Cn by 3. Let us assume that these are those molecules that are traveling parallel to x-axis and they have velocities C1, C2, C3, up till Cn by 3. Now out of all these molecules, I am going to consider only one molecule which has a mass of say m1, m and has a velocity of c1. Consider a molecule of mass m and velocity c1 moving in positive x-axis direction. Right? Now, that means it is going to start from one of the face. I'll just show you this. Let's assume that it is going to start from here and it is going to go and collide with another face here. Right? It is going to start from this face and this molecule is going to go and collide with this face. Right? It is moving parallel to x-axis. Right? Now, this is that molecule which has mass m and is moving with a velocity of c1. Right? Now, in that case, if it has a mass of m and is moving with velocity of c1, what will be the momentum possessed by this molecule? The molecule will have momentum. Molecule has momentum. Momentum is defined as the product of mass and velocity. The momentum possessed by this molecule will be mc1, right? Now when it collides, say this is my face CD AB, right? Now I can say that when this molecule collides with face B or ABCD, when it collides with this face, since we've said that when we are doing assumptions of gases, we said that the collision is going to be perfectly elastic. You're going to have perfectly elastic collision, right? I can say this molecule collides with face ABCD and will rebound with velocity minus c1. Why will it rebound with the same velocity? It rebounds with the same velocity c1. And why am I saying minus? Because if it was moving in this is my positive x-axis direction, when it rebounds, it will move in opposite direction. If moving outwards is positive, moving inwards has to be taken as negative. And why with the same velocity? I can say because the collision is perfectly elastic, right? So it will rebound with a velocity of minus c1 because the collision is going to be perfectly elastic. Hence, the momentum of the molecule after collision will be minus mc1. Momentum is mass into velocity. Now in that case, what will be the change in momentum? Change in momentum is nothing but final momentum minus initial momentum. Final minus initial. Final momentum we found out is minus mc1. Initial momentum is mc1. So the change in momentum will be minus 2 mc1, right? The negative sign indicates that the molecule has lost momentum during collision. The negative sign indicates that the molecule has lost momentum. The negative sign indicates that the molecule has lost momentum during collision. Right? Now, if it has lost momentum, then by principle of conservation of momentum, if the molecule has lost momentum, someone should have gained momentum. If the molecule has lost momentum, that means this phase ABCD must have gained that momentum. If the molecule has lost momentum, law of conservation of momentum says that the total momentum before impact should be equal to total momentum after impact. If the molecule has lost momentum, that momentum has to be gained by the body. Only then will the law of conservation of momentum be maintained. I can say therefore according to principle of conservation of momentum, therefore according to principle of conservation of momentum, if I apply law of conservation of momentum, I can say that the phase ABCD has gained equal amount of momentum, which is 2mc1. Why plus 2mc1? Because if that has lost its negative sign, gain has to be positive. Thus, I can say that the change in momentum on phase ABCD is going to be 2mc1. That will be the change in momentum on this particular phase. Now, the molecule is moving with velocity of minus c1 towards the opposite phase, and in due course it will go and collide with the other phase, that is OGFE. Right? Now, the molecule is moving with velocity minus c1. It is moving with velocity minus c1 towards the towards the opposite phase, right? Towards the opposite phase and collides with it, It will move to the opposite phase and collide with it. Now, due to this collision, again the velocity will be reversed, and again it will move with velocity c1 towards the. Due to the collision, the velocity will be reversed. Due to the collision, the velocity will be reversed, and again it will collide, and it will again collide with velocity c1 with phase ABCD. Right? So the molecule starts from this phase, collides with ABCD, comes back, collides here, again goes and collides, right? So every time it collides, the surface ABCD is going to gain momentum 2mc1. So I can say every time the molecule collides with ABCD, the surface ABCD will gain a momentum of 2mc1. That is the momentum that is going to be gained. Now, what is the distance covered by the molecule between two successive collisions? The distance covered by the molecule between two successive collisions is going to be 2L1 because it will start from one phase. Guys, can you just see this? It will start from here, will go and hit here, that is it will cover a distance of L, and then it has to again cover a distance of L to hit again. So the distance between two successive collisions is going to be nothing but 2L, right? It starts from here, it will hit, come back. So what is going to be your distance between two successive collisions? The distance between two successive collisions is going to be 2L1, right? Do we get this thing clear? Hits, goes, comebacks and hits, right? So the distance between two successive collisions is going to be nothing but 2L, right? Since it covers a distance of c1 per second, we said that the velocity, since its velocity is c1, it covers a distance of c1 in 1 second. What is velocity? Velocity is distance covered per unit time. Hence, the number of collisions on the surface. Therefore, I can say that the number of collisions on surface ABCD is going to be nothing but velocity divided by the distance, right? Now, once I know the number of collisions per second, number of collisions on surface ABCD is going to be this much per second, right? Once I have this, now I can find out the change in momentum. The change in momentum. The change in momentum of surface. The change in momentum of surface. Change in momentum on surface ABCD per second. The change in momentum per second will be nothing but the change in momentum in one collision multiplied by the number of collision. Change in momentum. Change in momentum per collision multiplied by the number of collisions per second. Change in momentum we found out is 2mc1. The number of collisions is nothing but c1 upon 2l. 2 and 2 gets cancelled. Therefore, the change in momentum is mc1 square upon l. Right? Now, this is for one molecule. There are n by 3 number of molecules that are going to collide with phase ABCD. Right? I can say similarly, other molecules with velocity, other molecules with velocity C2, C3, etc. will impart momentum mc2 square upon L, mc3 square upon L, and so on, right? Therefore, I can say that as there are n by 3 number of molecules moving along x-axis, as there are n by 3 molecules moving along x-axis, as n by 3 number of molecules are moving along x-axis, the total change in momentum on surface ABCD per second is going to be nothing but mc1 square upon L plus mc2 square upon L plus mc3 square upon L plus mc n by 3 square upon L. Each molecule is going to impart so much momentum onto the surface, Here I can take m by L common. If I take m by L common, this is C1 square plus C2 square plus C3 square plus Cn by 3 square. Right? Now, if I apply Newton's second law to this, by Newton's second law, rate of change of momentum, that is the change of momentum per second, is nothing but force. Change in momentum per second is equal to the force. Therefore, I can say that the force exerted by the gas molecules is going to be m by L C1 square plus C2 square plus Cn by 3 square. That will be the force that is going to be exerted by the gas molecules on surface ABCD. Right? Now, I can say that, but we know that C1 square plus C2 square plus Cn by 3 the whole square divided by n by 3 is nothing but CRMS square. The root mean square velocity is defined as the sum of the squares of the velocities divided by the number of terms added. Right? So thus I can say that C1 square plus C2 square plus Cn by 3 square is going to be C bar square into n by 3 cross multiplying. C1 square to Cn by 3 square is nothing but the square of the root mean square velocity into the number of molecules. I can substitute this in the equation of force. Substitute in equation of force. So in that case I will get F is equal to m by L C bar square into n by 3. Right? Now, but we know that pressure is force per unit area by definition. This is by definition. Force is nothing, pressure is nothing but force per unit area. Force we have already found out. Therefore, pressure is going to be force, that is m upon L C square n by 3 upon area. Right? But area, this can be written as pressure is 1 by 3 m C bar square into n upon length into area. Area is nothing but L square. So 1 by 3 m C bar square n L into L square. L into L square is L cube, and L cube is nothing but volume. Therefore, I can say pressure is equal to 1 by 3 nm C bar square upon volume. Right? Once I've substituted L cube as volume. Right? Now, I can say that the root mean square velocity is also called as your RMS velocity. I can say that what n into m, right in the beginning we had said is the total mass of the gas. Therefore, I can say pressure is 1 by 3 m upon v into C bar square. But m upon v, mass upon volume, is nothing but density. But mass upon volume is density. Therefore, I can say pressure is 1 by 3 rho C bar square. Right? So these are the different equations for pressure exerted by the gas molecule. So I can say therefore pressure is equal to Nm 1 by 3 Nm C bar square upon V. It is also equal to 1 by 3 m upon V C bar square. It is also equal to 1 upon 3 rho C bar square. We derived all the three. So this is the pressure exerted by gas molecule. Fine, do we get this thing here? Next. what do we understand by mean velocity? Now, what is mean velocity? Mean velocity is nothing but the average velocity of the molecules of gas in molecules of gas. It is nothing but the average velocity of the molecules of gas. Average velocity of the molecules of gas is called as the mean velocity. Thus, I can say that mean velocity is nothing but C1 square, C1 plus C2 plus up till Cn divided by n. Right? That is called as the mean velocity. Next, what do we understand by mean square velocity? Right? Mean square velocity is the average of the squares of the velocity of the gas. The average of the squares of the velocity of the gas, the average of the squares of the velocities of the gas molecule. Velocities of gas molecule. That means I can therefore say that C bar square will be C1 square plus C2 square up till Cn square upon n. This is called as mean square velocity of the gas. Next, what is root mean square RMS velocity? Right? Root mean square velocity, the square root of mean square velocity is called as root mean square velocity. The square root of mean square velocity is RMS velocity. Thus, I can say that RMS velocity can be represented as RMS velocity capital C is square root of C bar the whole square. So RMS velocity can be written as square root of C1 square plus C2 square plus Cn square upon n. Right? So these are the three different types of velocities that you have in gas molecule. Right? Okay, we'll stop this here for the day. Thank you very much.